All right, hi everybody. Brian, thank you for the great introduction. We're going to do a couple different sessions today in this seminar. We have 4 speakers. So as Brian went over the agenda, you'll see that it'd be great to cover a lot of different topics, but what's most important is we get questions from you and feedback, and then we can direct the conversation towards the parts that are most interesting. And so the first talk that I would like to do is using HALT in the product development process. So let's talk about HALT for those who aren't familiar with it. So it stands for Highly Accelerated Life Test, but it really should be Highly Accelerated Limit Test because it's not commonly used to actually measure life. It's used to understand the limits of the product when stresses are applied to it. And these stresses don't even have to be associated to normal use. And that's what differentiates it from a lot of other types of tests. And we're going to talk about the testing method itself, common ways it's executed, and how it can also be used in the product development process, because that's one of the most important aspects, is that it gains its most value used in specific parts of product development. So it quickly discovers failure modes. It evaluates design margins. This is very important for creating a mature product early. That word mature is very important, because that's what we're looking to do. If you go back to previous generations of product development, products are created and a lot of times matured in the field in version 2.0, 3.0, and the customer is effectively being a part of your reliability engineering team. Customers don't like it, it's not good for business. We're looking to mature the product, and this is a fantastic tool for doing that. One of the other really fundamental parts of it that's important in understanding it is it's not a test you want to pass, which is hard. We all want to pass tests. We've been taught to want to pass tests. And a lot of engineers take a lot of personal pride in their designs, and they want to pass tests so they can progress through the program. Well, HALT, if you've passed it, and by passing I mean you haven't experienced failures, completely wasted your time. There was no reason to do it at all. You want to fail. It's the failures and an opportunity to observe the failures, understand what occurred, and then use that as input to ruggedize the product early. So it's hard to get people to change how they think to understand that you're going to drive the product to failure. And where this pushback occurs is when you describe to them what you're going to do to their product and they say, that is unfair. Why are you going to do stresses so far beyond how it's used? Why are you going to vibrate it to 50 Gs when this thing sits on a shelf? And it's getting that connection to where you find out that the design engineers can transform from resistance to end up being the people who value the tool most. And I always find that to be interesting. It's always the people who resisted it the most who end up being the people that embrace it the most. And that's because they're most passionate about the product and they begin to understand the tool. So who do we want to be? Let's talk about who we want to be as we're doing HALT. You want to be this kid. This kid stole somebody's car and decided to see what happens to it when you smash it into things, rip the doors off. He might have flipped it, right? And the reason why I start off saying steal is you almost have to steal the prototypes because you want to do HALT as early as possible. And again, my focus is talking about how HALT goes in the product development process. And the earlier you do it, the better. But the earlier in the program, the more valuable the prototypes and the product are. So you really do almost have to steal it out from under people, destroy it, and then kind of ask for forgiveness. But when they begin to understand the process and the value you create, they will see how that was. They're glad you stole their car and smash it. So we're looking to test to fail, not test to pass. Now, some of the hallmarks of a really good HALT test, you'll notice here, is there's a fire department, there's safety cones, safety tape, and you got that smirk on the kid's face. So I've actually had 3 out of 4 of these in a HALT test I did once in a parking lot, because it was going to be so violent that we didn't want to do it inside. And we basically were almost able to sell tickets to other people in the company who wanted to see what we were about to do. So HALT really formally started in the 1980s. That's when it was introduced by Dr. Greg Hobbs, as Brian was discussing. And it kind of went slowly to where there were a few people that understood it to where it really became incorporated in the process. But through I'm always very interested in how products have been developed through the decades, going back 100 years longer, of how reliability has been a part of product development. And I found this one very interesting story in the 1960s. So the Apollo rocket program, being driven by Dr. von Braun in the 1960s, was one of the most ambitious engineering initiatives America had taken on. And there were a lot of challenges to overcome, but we had a commitment to have these rockets not only get us into space, there was a threat of, a competition with the Russians and this kind of sense of national security. We wanted to get a man to the moon and continue our natural drive to explore. The Apollo rocket, that cone almost stopped the entire program. That cone, they couldn't figure out how to have it not crack, even in testing. It's a very simple, looks like a very simple thing, but it's an unbelievable piece of science because it has to operate under insanely high stresses. It's effectively directing an explosion continuously. The conditions around it are changing dramatically with the external atmospheric pressure. It's not left under static conditions and they can optimize the structure for it. It deals with all kinds of vibrations. It goes on. And they couldn't make one that wouldn't crack. There was an engineer. It really was going to end the whole program. There was an engineer that said, all right, look, we keep testing it, we keep cracking it, but every time we observe a failure mode, it's different. We're having a hard time figuring out how to optimize the design. And he said, how about if we blow it up? And I'm not kidding. He took black powder charges. They put a channel into the side of it. They'd light off the rocket and then basically put dynamite in it and blow up the dynamite and shatter it. And through that, we're able to see the structural fractures that would occur over and over again in multiple patterns, and they ended up optimizing the design to where it could naturally dampen out any frequency put into it within 1/10 of a second. And you can still see this today. Have you ever seen the space shuttle launches when they show the cone and how the cone wobbles and moves until the flame gets set? Go watch those videos sometime. You can still to this day see that same technology in the cones we use today. And it was effectively the first HALT test, I would say. The first application of the HALT principle. Blow it up, look at the failure modes, let the failure modes be the clues at the crime scene where you murdered it that help you understand what's occurring. So I always thought that was kind of an interesting story where this principle was stumbled upon really 20 years before it became very well known. And this also leads to a new method that I've created, not necessarily invented, but have kind of formally labeled, and it's called use case 7, and we're going to talk about that later today. And you'll find that to be an interesting derivative of a testing method that is somewhere between HALT and overstress testing, but again, the same idea. So the equipment. So a lot of HALT testing is done in a HALT chamber, and Qualmark has always provided, they're really the creators of it. Dr. Greg Hobbs, who created the HALT method, is the founder of Qualmark, and they create chambers that create the vibration and the intense temperature swings that are very commonly used in a lot of regular product development. And by having a tool like this, it makes it very powerful to where you can do these tests very quickly, usually within about 3 days, and yield a great deal of information. And this is what the inside of one looks like. You can see electronics that are clamped to the table. You can see we've taken off covers. And again, we're not looking to see how the product will operate in normal conditions. We're looking to create extreme stress. That's why you take the cover off, so you can do temperature changes even faster. That's why you clamp it hard to the table, so you can get that vibration energy into it. None of that is how this product will really be used. You can see this is something that would probably just be on a shelf in a lab. But by, in the chamber, allowing vibration and temperature extremes to get in there as quick as possible, it's the same thing as putting the dynamite in the rocket cone. So there's two very important differences with a HALT chamber versus a regular environmental chamber. The first is the vibration. There's not single axis vibration. There's other vibration tables, but they tend to operate in 1 or 2 axes. HALT does 6 at the same time. So a single axis is more like a speaker, where you have a specific frequency and you apply it in a single axis. But if we're looking to as quickly as possible create failures, and not looking for a specific relationship between a single frequency or direction of a stress, you want to get as much in there as possible. So it will do it in all three axes, linearly and rotationally at the same time. And this is where an amazing part of the technology comes into play with the table. Broadband frequency. It does multiple frequencies at the same time in all 6 axes. And that's where the technology of not just vibrating it by putting something on that's oscillating and having it be transformed, that energy through the table, makes a big difference. The thermal. In a HALT chamber, we often have liquid nitrogen. Well, you have to have liquid nitrogen be what drives the cold, and you have very high electrical heaters that drive the hot. Now, in a regular environmental chamber, you usually have compressors that drive hot and cold, but they cannot do it at the rate that's necessary to create the thermal expansion stresses. We're looking to create mechanical stresses from different thermal expansion coefficients and volumes that will have a thermal gradient across it. So having liquid nitrogen is key. That's the only way you can get those kind of fast temperature transitions. And we're going to be talking later, we'll be having some talks from some specialists with regard to liquid nitrogen and how it can be delivered effectively. So let's talk a little bit about the principles of how this work with HALT helps the product. So if you take a look at this and you these 3 lines for stress on this axis, the operating specifications for product high and low will be that center section. You then have the next of the operation limits, and then you have the actual destruct limit. The operation limit's where the performance falters, but when the stress is removed, it recovers. The destruct limit is where it cannot recover, it gets destroyed. So these are your margins for stress. So if you are saying that the product can handle those operating specifications is what you're communicating for the actual use in the field, the difference between that and the operational limits are the margins you have for stress. So the variability of how it uses up those margins, right? And as you use up those margins and you come to the limits, that's where you find failure. Because of course you can't control the environment it's really used in or how it's used exactly. So you have variabilities around all of these. You have variabilities of the stress applied and you have variabilities of the actual products and what stress they can handle. If you look at any kind of quality output, when something's manufactured, there's variabilities in the assembly and its strengths. So there's going to be part of the population that pass that are the weakest and some that are the strongest. And that's what this green area is. This green area is all the variability of the individual units. And as you can see, they have all passed their upper and lower limit, which is maybe how the quality system is set up, is to not let anything pass that's beyond that. But if you look at the variability of the stresses from the upper and lower limits, there's a set that it crosses over. And that area is your failures. That's your percentage of failures. So there's a couple ways to address this, of course, right? You have 2 strategies. One is to control the variabilities here, and the other is to control the distances between the means and those variabilities. Well, good luck controlling how the customer uses it in the exact environment it's operating in. That's very difficult to do. And you've already put a lot of money into controlling the manufacturing, and the tighter you try to make it, the more expensive it becomes to manufacture. So this is where HALT becomes extremely valuable. Because with HALT, what we look to do is find those failures and change the limits to where the product fails by having quickly discovered what they are through extreme stresses, making design changes that mitigate them. You've now put much larger margins in there. So now your failures are much smaller. And that's the basic principle. We're creating larger margins on stress because we very quickly found out what the failures are, and then we made design changes. And we did that without increasing expense to manufacturing and quality screening or trying to further control the way the product is used. So this is the bathtub curve, which we're all very familiar with regard to how we kind of generically characterize product usage. Who's familiar with the bathtub curve? Okay, good. Almost everybody in here. So the bathtub curve is describing what happens with regard to failure rate for a population that's put into the field. So this is generic. Real ones are obviously very different. But it's saying that you have a lot of infant mortality, right, with quality defects, and that those quickly are exposed and removed from the population. So ideally you would, this is from the first time you turn it on, so you do your burn-in and your HAS testing to here, and then give it to the customer, hopefully around here is actually when it's released. And then you hope for a somewhat constant failure rate for a lot of its life. And the constant failure rate's always kind of generically assumed because you have a lot of individual behaviors in a product, and when you put them all together, you kind of, if it's a complex product, can say it has X failure rate over its life is an easy way to measure it and communicate what's going to occur. And then at some point later in life, all these units begin to fail at an increasing rate. They're wearing out, and this will continue until the entire population has worn out. So that's a kind of generic way to look at reliability for a group of products. Now, what can HALT do for this? It can help with all three phases. It reduces the sensitivity to quality manufacturing issues. If you recall at that previous curve with the distribution, if you create more margin, the units that are kind of falling farther out on those quality specs now are less likely to run over into systems that have the stresses that expose issues. And HAS testing, which is highly accelerated stress screening, is one of the most advanced ways to do a quality inspection in production, is a derivative of HALT testing. You cannot create a HAS profile without having done HALT testing in product development. So it helps greatly there in the first part of the curve. Next, it will reduce the sensitivity to stresses during use life. We've created that margin. So now the stresses that are occurring that drive that random failure rate affect a much smaller part of the population. So we've lowered the center part of the curve. And then the last is it increases time to wear out, because wear out is accumulated stress that causes a performance issue. So if we created more margin, it's much more likely that if accumulated stress causes that failure, you have more of the strength of the product to go against that accumulated stress, and it can last longer. So what we've done is turn the bathtub curve into that. We've shortened and made it easier to have units that pass quality inspection and survive well in the field. We've lowered the random failure rate, and we've stretched out the time to wear out. So through this one test, we've affected all three major phases of a product's life. So what's the process? How do we do HALT? First thing we do is we apply the stresses in the test. And again, these stresses don't have to be associated to standard use stresses. They can be any stresses we come up with. Dynamite in the middle of the cone. It doesn't occur when a rocket takes off, but it was a stress that provided information regarding how the design fails and operates so they can make it stronger. With these failures, we collect them. We're like detectives. We've created a crime scene, we murdered the product, and now we want to do a really good job of collecting all the information of the failures that have occurred and when they occurred and with what stress applied. Then we want to analyze it, because we want to turn these observed failures into information engineers can use to improve the design. And then we improve it by having design changes that directly address those failures that happen in those stresses, and we can take the process around again and apply stress again and see how much it has improved, and then we can choose if we want to go farther and continue the process, and it continues as a cycle. So, with regard to the product development program, is to do it as early as possible. And this can be very clearly communicated with a very important principle called the rule of tens. And this puts you in the awkward situation of campaigning for prototypes. So we need a really strong case, because usually they're gold, right? They can cost, you can have $1 million prototype because it's handmade, it's tested out new technology, and it's not part of any manufacturing process. It can be very expensive. And it's also, a lot of its value is the fact that other people need to get information from it too, right? Prototypes are made for a lot of reasons. So what's our case for saying, hey, give us to one, with that picture of the kid in the car, the first car that came, the first prototype put together, they're like, oh no, I'm just gonna take it out to lunch, and you bring it back like that, and you're like, well, I kind of meant to. What's your case? Your case is the rule of tens. The rule of tens simply states, and I'll be honest, the first time I heard this, I thought it was pretty hyperbolic, but actually in practice I've seen it's very conservative. It simply states that for every phase in a product development program that you find an issue, it costs 10 times more to fix it. 10 times more just per phase. That means we're talking about 100 times more, 1,000 times more, 10,000 times more cost to fix something for every phase you find it. All of a sudden, you're making a really good argument for them to give you products to find an issue as early as possible. So, okay, what if you had found an issue in early design phase through testing or some other method? It might just be simply a matter of changing a design in CAD and adjusting a prototype or just a part. And you can imagine that's something that's a few dollars, right? You can measure that in engineering time, a couple hours of engineer's time, maybe the machine shop a little bit, right? So let's say that's just a few $100s possibly. Then if you were to catch it later in integration, you might be actually scrapping molds that you made. Right? This can get very expensive. And you've also had a lot of other processes and systems made around that design, manufacturing, cost reduction, and those might have to be changed too. You can see how that easily could be 10 times more in cost. Well, then let's go on to the next. What happens when you catch something late in the program? You're delaying release to fix it? What does that cost? Right now you're going in the cost that go in the whole other outer shells, right? Market opportunity loss, and all the other peripheral things that have been done around it that now have to be reset and redone. And then, of course, what does it cost to find a problem in the field? This is where the cost gets epic, right? Because this is where you're scrapping huge amounts of product, and that's after you've solved the problem. You have engineers going in the field to find the issues. You have customers that are down. You have sales that are lost. I mean, you start to see how this rule of tens is actually quite conservative. The picture of finding something in that phase costs 10,000 times more than finding it on the design table. That's your case. That's what you talk about, and that's how you get prototypes allocated for HALT testing early in the product development process. So let's talk about how things are integrated. So for reliability integration, it's the process of seamlessly integrating reliability tools together to maximize reliability at the lowest possible cost. That's our goal. That's what we're trying to do. So let's look at a typical product development process. There's a lot of tools that are integrated through the process. These are all reliability tools that you might include in the concept phase, design phase, proto phase, or manufacturing phase. So you can see I actually listed HALT 3 times in there. Remember, HALT's a circular process. You want to keep using it. You want to continue to get this information about the product with regard to how it reacts to stresses and changes that have been made in the design, because there's changes that have been made in the design that are driven by other initiatives like cost reduction, manufacturing, maybe last-minute feature adds or removal. And this can affect performance. I mean, one of the mantras of reliability engineers is there's no small changes. That can be a little hyperbolic. There are small changes, but the basic principle is important to at least acknowledge and discuss when changes are made. So HALT also doesn't just stand alone. It interacts with these other tools that are in the program, and it's important to keep that interaction. What's driving your reason for the HALT testing? What is the output? Where do you take the output from the HALT testing that you executed? So some of these other tools that it very commonly interacts with is FMEAs, failure mode effect analysis. The idea with an FMEA is to speculate as to all the types of failures that could occur, what drove it, what the effects are, and then to create actually a quantitative ranking system of severity, likelihood of occurrence, detectability, and rank these different failures. And then that will drive actions, and some of these actions might be HALT testing. You have fault tree analysis, and this is having a specific failure and trying to understand the root cause. So again, you can see very easily how this links to HALT testing. You found a fault and you're trying to understand it. Well, that's one of the purposes of HALT, to find faults for you to analyze. So you can see how it very clearly links to this tool. We also have design of experiments. This is another interesting aspect of how HALT is very helpful. One of the important parts of design of experiments is you're finding interactions of stresses. Without design of experiments, we typically apply a single stress and look for a response, then a different stress and apply a response. What about the interactions of stresses? You need design of experiments for that. Well, what does HALT do? It allows you to apply combined stresses in a single test. So you can see how that links very well and are often used together. And stress strength analysis, right? This is about investigating margins. So let's take one of these and talk about it a little bit. Let's talk about FMEA. How could they possibly interact with each other in a specific example? Well, we have the key quantitative parts of FMEA. You have the severity ranking, likelihood of occurrence ranking, and the detectability ranking for a specific possible failure. And this leads to the RPN number, which is the risk priority number, which is the product of the other three numbers. And this is the number that in the end we sort from greatest to least for each of these line items. Now we know where we should put our resource. We can never have enough resource to apply to all the issues that we believe will happen. So we need a way to apply it to where it matters most, because at some point you just run out of resource. And that's why this is so valuable. So let's imagine that in doing this, we had one and we found that our top one, the remark was, we need to build a bench setup for downstream pressure sensor to identify stresses. This was going to drive one of our biggest concerns of failure, which was incorrect pressure. And let's say this is a medical device. Incorrect pressure can give a doctor information where they killed a patient because they are not understanding what's happening. So it's not just an inconvenience, it can be life or death. And I've actually experienced this type of thing regularly with medical devices and simple sensors that are giving, these are sensors that are disposable, by the way, right? A lot of medical products, they have components that are disposable that, especially if they interface with the patient, right? Because that's one of the easiest ways to deal with being sanitary. So here you have disposable sensors that if they give the wrong signal, you can kill somebody. Okay, so that's come to the top here. Well, at first we said, okay, we'll do some benchtop testing. And then we said, wait a minute, what about HALT testing? What about if we take the sensor and find every possible failure mode and the parts around it? Where are the sensitivities that could be affected by manufacturing or use? Again, medical devices with patient interaction, extremely difficult issues for defining use case and environment for a reliability engineer. Why? Every body's different. Every doctor's different, right? And it becomes very difficult to characterize. So one solution is to create those large margins. So we do a HALT test. Now we know a specific area of interest, and we put accelerometers in that area for vibration to see how the sensor begins to fail and the assembly around it. And what we discover is that not only did we get good information about the sensor, but we found a nice surprise. We also found out that there's a PCB board connection that can easily disconnect. We didn't even know we were looking for that. We were really surprised. We're like, holy crap, that thing just pops right off. And remember I said it's hard to characterize how a doctor uses something in the patient and what's happening? We really realized how high a risk that was. So through that, we actually changed rankings on a different line item that was much lower. It had a ranking of 50. And now with the new ranking, for likelihood of occurrence of that being higher, it actually ended up rising right to the top. So we realized that, of course, if you're sitting down as a team and hypothetically looking at failures, that then they get actual data, we realized, wow, this actually was a much more serious and should be addressed. And we found that in HALT testing as opposed to finding it from field data and field feedback, which is much more difficult. So I think our work is done here talking about the HALT testing. I see a question back there.
Yeah, just in context of basically, the FMEA coming up with the RPM and things like that, I'm wondering basically how does sample sizes come into play here in terms of kind of evaluating, right? I mean, you got to have a certain confidence level on the outcomes.
Yep.
So I was wondering if you could basically address sample sizes, and then also if you might be able to make a few comments about Weeble statistics in the whole issue here concerning HALT testing.
Sure, yeah, that's great. So the question was, how does sample size come into play with HALT testing with regard to, getting the variability and confidence, statistical confidence, and then with regard to that, using it as input for viable testing? Well, this is another thing that differentiates HALT from a lot of other testing, is the reduced criticality of sample size. And this goes with that principle, again, of we want failures. We're not looking to draw statistics on percentage of pass and fail. We're hoping to fail every single unit. We've taken the stresses to a level where it's hard to make a case for how this would fail in the field, right? I mean, if something sits on a shelf in a lab, how do you correlate statistical likelihood of failure for 50 Gs of vibration shattering something, right? So that's what we've given up for the speed of getting to find out what failure modes look like. I mean, think about, again, the Apollo rocket cone. Putting dynamite in there, how would you correlate those failures to anything in the field? So that's a big difference. We're actually not looking to make any statistical statements on likelihood of failure. We're looking to only see the failures, and that's what you've given up for the speed of getting that very valuable information. So Weibull analysis is the input data sets are based on the idea of percentage that passed and percentage that failed, and looking for how those behaviors change and characterizing and projecting it out. So I would be very hesitant to use any HALT data for anything like that, because that's not its purpose. It's possible, but the research project you would have to do in advance would be quite tremendous to make those correlations. And you would be better to do other more traditional type of reliability tests to generate that information. If you develop the same kind of product over and over again, if, let's say, all you developed was rocket motors and you've been designing rocket cones for 60 years, there is value in doing in parallel to a product development program those kind of research projects to where you glean that information from a HALT test. But in most product development cycles, that would not be as cost effective.